I only got one from Adam.
Oh, you got one? Okay, perfect.
Before the lesson started.
Oh,
Okay,
I've got
very
this
good.
one.
Okay, nice. Pass it along then.
Do you guys want to give me nothing for this?
Okay.
So great.
Cool.
So as long as she's on ground level, she should be fine. Yeah.
Okay.
Yeah.
Sorry to bother you. Can I have like 4 copies of the year 11 exam paper? Just blank copies.
Okay.
Yeah, thank you.
So let's say 10 when it's literally 0.
All right, guys, I'll give you materials for the day now.
Oh, yeah, that's your idea, right? You do it. Wait, Jerry.
Yeah. Okay, so like a little bit earlier, I like recorded an exam review already, so that should go through some of the questions. But I guess if you guys wanted earlier, like I'll like try to wrap up today's content earlier, so you guys have time to ask about exams.
He probably gets like all the
We could clarify that.
No worries. Does anyone else need a copy of the notes? Think you guys are still missing one? All right. Anyone else missing homework? Yep, homework. Okay, like all of you guys. No worries. Yeah, of course.
Thank you, sir.
No worries. All right. So does everyone have a copy of the class notes?
Yes.
The homework? Exam solutions? All right. Don't. Okay. You do? Okay. Brilliant. Hello, can you? If you have any questions, of course, like just ask from online. Yeah. So just type in the chat.
I'm genuinely considering if I'm
What's your subject?
Huh?
What's your subject?
Echo.
You're right.
I'm like rank 3.
Say D. It's not B, it has to be D. It's not D, it has to be because they're polar opposites. That's kind of rough.
Lovely.
Like, even if I'm like rank 1 echo, it's echo.
Oh,
No, but it kind of makes sense.
Yes, we'll be starting. I just need to hand out one more thing.
It's
Yep.
still, for question 2, it's separated like.
Question about exam?
Yeah.
Yeah. If anyone has a question about the exam, please save it for the end of class. I'll try to wrap this up soon, but we just have to get through today's content first. Besides, there will be an exam review that's coming out soon. That'll be going through the MCQs as well as some of the short answer questions. Okay. Yes, this is Fizz. All right. Guys, can I have your attention, please?
Yes.
So, I know there's a couple of you guys who are new. Have you guys been to Zhang's before?
Yeah.
So all of you guys know about like the Zhang's like quiz, homework, extension classes, all of that?
Yeah.
Yes? Okay. In that case, no need to go through that. But for those of you guys who are new, please record this link down, or like just type it into like your laptops or your phones right now. So that will lead you to our Google Drive where I upload all of my slides and stuff every single week. There's also like additional practice questions, and when you guys start year 12, I'll upload like some other stuff on there. For example, like past papers, trial papers, all of that. Okay, so very useful drive. Please have the link saved. Yep, Z-H-E-N-G. Sorry, guys. But maybe just type this into your phone first, just to make sure it works. Otherwise, if you write it down, sometimes you get home, you don't really know what you wrote. Yeah, so just sign in with your Google account, request access. I'll approve it on my end straight away. Just let me know once you've sent through the request. Yep, okay. So if you refresh now, you should be able to see everything, including this week's slides. Okay, brilliant. Yep, Oliver got yours, Sai got yours. Insert name, I also got yours. Who's insert name? Okay, probably.
I haven't done this for quite a long time.
You haven't done what, sir?
I forgot to re-add myself after my school.
Oh, that's right, yeah. Do you still need the link up here or no?
I've got a copy it down.
Okay. Maybe just take a photo of it, because I'm going to rub it out soon. Alright guys, we'll get started with this week's content now. So, here's an overview of what we're doing this term. The first 2 weeks, we're just going to be finishing off the final inquiry question of Module 3. So some thermodynamic stuff. And then for week 3 onwards, we're going to be doing Module 4. And we'll be finishing off all of Year 11 content by the end of this term. So next term onwards then, as you might expect, we'll be starting Year 12, so Module 5. So yeah, be very much looking forward to that. In 2 terms, you guys are going to be in Year 12, so very exciting times.
Wait, what's up to week 5, or is it like just the rest?
Oh, just the rest of Module 4. I couldn't be bothered to type it out. Yeah. Oh, sure. Yeah. So for Oliver, Sai, have you guys refreshed and checked that it works?
Yeah.
Okay. Just make sure you save the link somewhere so you don't forget about it. Perhaps like self-text the link, something like that. But yeah, have a poke around the drive. There's a lot of useful things in there. Okay, so sign-in reminder. I think all of you guys know how to sign in, and hopefully you have signed in as well. Right, so what are we doing today? Today we're doing thermodynamics. So, I mean, this week and next week are both about thermodynamics. So first of all, like, what is thermodynamics? It's kind of about the transfer of energy, right? So next week we'll be looking at concepts like conduction, convection, and radiation. So those are terms you would have heard of before, even from like junior science, but we'll just be doing them in a little bit more detail, introducing some equations where appropriate and doing calculations. Yep, so you'll often find a lot of science is just building on previous content that you've kind of seen before, although not in full. Yeah, so that's kind of next week. It's about how heat can get transferred from one thing to another, right? Like conduction, like hot thing, touch cold thing, heat transfers. Convection, you can get like convection currents, whatever, in any sort of fluid, and that can be heat transfer. You can also get radiation, which is like, for example, the sun, it radiates out some light energy, heat energy, all of that, and that arrives on Earth. So that's how heat is transferred from A to B. And what we're doing this week is more so about what happens when the heat gets transferred from A to B. So we're kind of asking ourselves the question of, okay, if like this thing now has more energy, if it's got more heat now, then what's going to happen to it? And it's going to be one of 2 things. Anyone want to take a guess? If I transfer energy into something, heat into something, what might happen? Just
might break.
Sure. So we can get a change of state.
Particles vibrate.
Yep, particles vibrate. And do we know what that corresponds to?
Greater kinetic energy.
Yeah, which corresponds to?
Greater temperature.
Yeah, okay, yeah, great. So you guys already have like a nice picture of this lesson. But yeah, when heat gets transferred into something, either we get an increase or either we get a change in temperature or we get a change in state. So say from solid to liquid. Yeah, so that's what this week's about. We'll be going through a brief intro and then some terms that allow us to do some calculations. Okay, so the first idea that kind of underpins everything is something called kinetic theory. Now here, don't worry about like every single one of these little details. It's not that useful for exams. But if you want to memorize it, like by all means, go ahead. The point of this really is to give you a mental picture of how you can imagine temperature, essentially. So kinetic theory basically says, okay, like gases, a bunch of different molecules. We represent them as these identical balls, and they go in constant, rapid, random motion. They just keep moving. And when they move, they are going to hit the walls and also each other. So I guess like kind of going on a tangent, that's what creates the pressure. So if you have like some sort of air in a balloon or whatever, they'll bounce around, they'll push on the walls, and that's what gives you the pressure. Okay, so specifically, I just want to bring your attention to the fact that every time they hit something, it's always going to be an elastic collision in this case. Do we remember what that means?
Kinetic energy is conserved.
Yep. So the kinetic energy is conserved, not just the momentum, right? So in all collisions, momentum is conserved. But in elastic collisions specifically, kinetic energy is conserved also. And why is that significant? Because remember, the kinetic energy, so how fast these particles are moving, that is what we interpret as temperature. So what this is really saying is that temperature is not really being lost through those collisions. Okay, so next idea is a pretty important term that I want you guys to be able to use, and that's thermal equilibrium. So the whole point of this concept is that if you have two objects and they are at different temperatures, they come into contact. In that case, you'll get temperature transfer, well, you'll get energy transfer from the hotter to the colder object. And that will keep happening until they reach the same temperature. And it will often be some middle temperature. Sorry, guys. So let's say something like 0 degrees, something 20 degrees come together, then maybe overall they'll reach around 10 degrees or so. So in this case, the concept itself isn't too insane, but what would be useful to do is if you guys can use kinetic theory to explain how this whole thing happens. So if we kind of visualize two objects touching, one is the hotter object, one is the colder object. So when it comes to the hotter side, they're all high velocity. Colder side, they're all going to be going a little bit slower. And because they're in contact, what can happen is you can have like a really fast moving one hit one that's relatively slow moving. So that occurs at the interface between the hot and cold object. And when you get a collision between a fast and a slow thing, then the fast one is going to slow down and a slow one is going to speed up. So that's kind of the process of the energy transfer. So fast, one slows, slow, one speeds up.
So is it also all particles have the same kinetic energy?
Yeah, exactly. So they're going to all keep colliding with each other until across this entire like two objects that are touching, they reach the same temperature, so thermal equilibrium. Right. Cool. So that's what I'll talk about for now. I'll come back to this idea a little bit later as well. There's something else I want to talk about. But for now, just keep this picture in your mind. With kinetic theory, you can use it to visualize this process of energy transfer from hot to cold. Okay. All right. So next is two terms that might sound pretty similar in daily life, but they are actually quite different. So that's heat and temperature. So for our topic here, heat and temperature are completely different quantities. When it comes to temperature, temperature more so refers to the state that certain objects are in. So we can say like this certain object has a temperature of like 20 degrees Celsius. This other one has a temperature of 30 degrees Celsius. Whereas for heat, heat is specifically used to refer to energy transfer. So say when we have that hot and cold object touching, then what we can say is that heat is transferred from the hotter object to the colder object. So that's why here they call like heat a process, right? It's not really something that an object has. The thing that the object has, we call that temperature. When it comes to heat, we specifically mean the thermal energy that is transferred from usually the hotter thing to the colder thing. Just notice here as well that when it comes to temperature, it's denoted by capital T, and the unit is, as you guys are used to, say like degrees Celsius. Okay, guys. I'm not sure why no one has like pointed out this mistake before, but it's meant to be degrees Celsius, not Celsius degrees. Okay. And when it comes to heat, heat is denoted by the letter Q. And if you look at the units of heat, it's actually in joules, right? If you ever see joules, think about energy, think about work, right? So here, heat is thermal energy that's being transferred from A to B. So that's why it's got these units, right? So notice temperature and heat, they have completely different units because they have different definitions in this context. Okay, so for temperature, I just want to say as well, it's specifically the average kinetic energy of particles, right? What does that imply? That implies not everything has to be going at exactly the same speed. Thank you. I think we have enough homework. Yeah, thank you. So who needed the extra exam papers? Okay. I think there was a fourth, sorry. I think there's a fourth person that wanted an exam paper. Empty exam paper? No? You already? No, you guys all have one. Okay, cool. I guess we have an extra one that I'll do on the way home. Yeah, sorry. So back to this point. What this kind of implies, right, is that even within a system that's at thermal equilibrium, the different particles inside, they are actually traveling at slightly different velocities. Yeah, so... Yeah.
Are you still there? Oh, no. Can you go back to the previous?
Yeah, sure. But yeah, like even within the same object, the average kinetic energy, that might be the same, but the individual kinetic energies are different. So if we have if we have two objects and they're in thermal equilibrium, can we say that there is no more energy transfer between those two objects? We actually can't. So you can have two objects that are at the same temperature. So maybe they are both like 10 degrees Celsius. But what this implies is that the KE average is the same. So maybe it's got like one that's like this, one that's a little bit faster, one that's a little bit slower, and same with this one over here. Right, so even within these objects, they can be slightly different velocities. It's just that they average out to be the same thing, so their temperature is the same. So in this case, right, you can still get the faster moving one here, colliding with the slower moving one there, and so you can still get energy transfer. right? So how do you properly distinguish that idea? So you should say thermal, actually we have this word here. We should say that at thermal equilibrium, there is no net energy transfer. So I've actually seen that sometimes as an exam question where they try to trick you, right? So the exam question was something like one of the answer options was that, okay, at thermal equilibrium, there is no energy transfer. But that option is actually incorrect because there is energy transfer. There is just no net energy transfer, right? You can still get the faster one here hitting that slower moving one on the other object. But at the same time, you can get the faster moving one from object B hitting the slower moving one in object A. So you will still get energy transfer, but it will be exactly the same, right? A transfer to B exactly as B transfers to A. And that's at thermal equilibrium. Yeah. So point being, just make sure to look for this word. That's the most accurate way to say it, is that there is still energy transfer, just no net energy transfer. Okay, this next point here is a little bit of a minor point. Doesn't really come up in exams that much, but it's nice to learn about anyways. So the key idea here you have to appreciate is that work and heat can be interconverted. And when we say work, we mean like the work that we studied in Module 2, that work. Cool. So we're just going to look at 2 case studies where first we show that work can be converted to heat and then heat can be converted to work. Okay, so first we have this experiment here. That's called the paddle wheel experiment. And it's done by James Joule, the guy that we named the unit of energy after. So essentially what we have here, right, if you look at the setup, you have masses that are wound along a string, along this like center spindle. So what can happen is, as like one of these masses falls, then it's going to start to spin the center thing. And when that thing spins, it's attached to these like light gray paddles, and that paddle will begin to spin in the water. And what we actually noticed was that when that began to spin in the water, the temperature of the water actually started to rise a little bit. Right, so what we have, first of all, is that as the mass falls, GPE tends to KE, and then the paddles will turn, so that's the work that's being done. And then what happens is that the temperature of the water increases, so that's your heat. Cool. Has anyone ever used like a blender before? Like those really fast blenders, like you might make a smoothie or something with it. I'm not sure if you guys have noticed, but like this effect was quite obvious at the one for the blender I have at home, where I like dump some water into it, I like lock it, I like put it onto the thing, it like the blade starts spinning really fast, right? And what I notice is after like maybe 10-20 seconds, then the water actually starts becoming warm, right? And that's literally because of the really fast moving blades cutting through the water, right? It's literally like slapping the water molecules, right? So it's like literally giving them the kinetic energy. I know that's a funny way to put it, but it's a fair way to imagine it, right? You have that really fast moving blade, kinetic energy. It's going to give kinetic energy to those water molecules, right? Because if you want to blend something, you need it to move. And to get it to move, like, you know, there's some kinetic energy in there, and some of that goes into raising the temperature. So that's kind of what this is about. Okay, now going the other way, so heat can be converted to work. Power plant is definitely the best example of this. So when it comes to power plants, right, just so you know, pretty much every like method of power generation, they work the same way in that they end with some sort of turbine being turned, right? So maybe you guys have played with those things where you can like turn something and then like the light or like the fan starts spinning, right? So this is Yeah, kind of like those things. But that's the whole point, is that at the end of any power plant, what we want is to have something turn this turbine. And then when that turbine turns, it can actually convert that kinetic energy of that turning into electrical energy. And we can harvest the electricity to like power something up, or we can use it to charge a battery to use later, all of that. So turbine is where we usually end. So that's like the first thing that is common between a lot of power generation methods. Another thing that's really common is that most of these power generation methods, they are literally just like giant kettles, right? Like it doesn't matter if it's like a coal power plant or like a gas power plant, whatever, or like even a nuclear power plant. All they're doing is they're generating some heat, right? You're burning coal, or like you're burning the gas, or you have a nuclear reaction that generates some heat. And what do we use that heat to do? We use that heat to turn water into steam. And why do we want steam? Because steam wants to rise. It's got motion, right? So if we put a turbine right above the steam, then on the way out, the steam has to turn the turbine first, and then we can harvest the energy that way. Yep, so that is the heat being converted into work. You have the heat from like nuclear reaction, coal, burning coal, whatever, boils water, steam push turbines. Cool.
Does heat necessarily rise, or does it just like expand in all directions?
Wait, here it's a steam that rises. With the heat, it's just referring to like the heat from say like burning coal that gets transferred into the water to make the water change state. So it's like what you said earlier, right? How like when things get energy, they can change in state.
Yeah.
Yeah.
The steam rises then, but is it like forced to just rise by the design of the structure itself, or does it expand in all directions?
Well, it's just like lighter, right?
Yeah.
And also it's like really hot, and because it's hot, then like really high kinetic energy. So those particles are literally bumping around everywhere, and so naturally, as they bump around, they'll like bump to where there's less particles, which is like the atmosphere. Yeah. Okay, so measure of temperatures. You guys need to know these two units, Celsius and Kelvin. Fahrenheit, yes, it exists. Don't worry about that though. But yeah, so we have the Celsius scale and also the Kelvin scale. So the Celsius scale is, of course, the one we're more familiar with. With the Celsius scale, it's calibrated on water. So it's very much focused on water. What we did was we kind of looked at, okay, like what temperature does water freeze at? And then we define that as 0 degrees Celsius. And then we go, okay, what temperature does water boil at? And we say that's 100 degrees Celsius. And then based on like the differences between freezing and boiling point, that's like 100 increments of this unit. And so that kind of decides one increment of this unit. Yep, so it's literally just designed by looking at water. So sometimes like we refer to Celsius as the unit that expresses how hot water feels. And then we say like Fahrenheit is how hot like humans feel. And then for Kelvin, it's about how hot particles feel. And I'll explain what that means in a moment. In fact, I'll do that now. So when it comes to Kelvin, Kelvin is an interesting unit in that for Kelvin, the lowest point it can get to is 0 Kelvin. So of course for Celsius, right, you can go negative. You can have like negative 20 degrees Celsius, but you'll never have negative Kelvin. Kelvin, the lowest temperature is 0. And that's because Kelvin expresses the movement of particles. So 0 Kelvin literally means all of those particles have stopped, right? So if you go back to the very beginning, you imagine that this one, all of those particles moving around. Here they're moving, so it's some positive Kelvin. 0 Kelvin implies a point where all of these particles have literally frozen in place, they've stopped moving. And there's actually a special name we give to that point that you might want to learn. It's called absolute zero. Okay, so absolute zero is the lowest possible temperature that anything can reach, because at that point, no particles are moving at all, and you can't have particles like going in negative motion. That's not a thing, right? So not moving is the extreme. Now, I guess I'll ask you guys the opposite. Do we think there's an upper limit in terms of the Kelvin unit? Yeah, there really isn't. Well, yeah. So when it comes to like you can have like a minimum extent of them not moving, but when it comes to maximum extent, it can go really, really far. They can move like faster and faster and faster. And remember, for the kinetic energy, it's kind of extension, but it doesn't have to be translational. It can be like rotational, vibrational. But yeah, don't worry about that if you've never heard of it. It's not useful. Okay, so that's why we say like Kelvin is about how hot particles feel, right? Because it's kind of calibrated with that mental picture of those particles moving, where 0 is they're not moving, and anything above that is that the particles are moving, and a higher Kelvin means that they are moving even faster. Okay, so that's kind of the theory behind these units. Now, the more important thing is, like, what does it mean for us in practice solving questions? First of all, you need to know how to convert between kelvins and Celsius. So it's actually relatively simple. To go from Celsius to kelvins, you just add 273. If you guys want to memorize this extra detail, it's technically like 0.15 as well. But that won't make too much of a difference in terms of doing questions. Okay, yeah, so at the freezing point of water, that's actually 273 kelvins. At boiling point of water, 100 degrees Celsius, that's 373 kelvins. Okay. All right. Now in terms of when we use each one, so remember how we have this concept of like SI units that we prefer to use in physics. So like for mass, the preferred unit is like kilograms. For lengths, the preferred unit is meters. Here for temperature, the preferred unit is going to be Kelvin. Okay, so if you ever do anything with temperature in physics, Kelvin is going to be the preferred unit. A lot of the equations you'll learn, especially in year 12, if they involve temperature, you have to use Kelvin, otherwise it's not going to work the same. Okay, one last thing I want to say is that Celsius and Kelvin, they conveniently share the same increment. So what I mean by that is like, if we say something is now 1 degree Celsius hotter, that is equivalent to saying it is 1 Kelvin hotter. Okay, so 1 Kelvin and 1 degree Celsius is exactly the same. So what is the difference? It's just that degree Celsius and Kelvin, they have a different starting point. Right? It's kind of like they have the same gradient, but the y-intercept is just different. Right? So for Kelvin, it starts at 0, whereas for degree Celsius, that starts at negative 273.15. Okay, so yeah, just to quickly summarize what's necessary, please memorize the conversion that's not on your data sheet. And also please know that in general for phys, if you do a calculation, use Kelvin. Okay, so we're about to be ready to dive into the more interesting parts of this lesson. We're pretty much done with all the definitions and stuff. There's one more thing I want to teach you guys, which is a concept called internal energy. Now, this is not in the syllabus, so you won't be tested on this explicitly. But the reason I'm teaching it anyways is because I think that understanding this one extra concept actually makes everything else stick a little bit better. So I'm going to teach it to you guys. If you guys end up finding this concept kind of useless, just forget about it, okay? But I'm sure there's at least some of you guys that will find this helpful. Yeah, it kind of is. It kind of is. But But yeah, when it comes to internal energy, first of all, that is represented by capital U, but that doesn't really matter. All that matters is that for internal energy, think about it as the total energy contained in a thermodynamic system. That's quite abstract. What does the thermodynamic system mean? It can be something quite abstract. You can turn into something more concrete. For example, like it can be like the water in a kettle that you're about to boil. You can consider that as a thermodynamic system. Or if you choose to, though I don't know why, you can include the water plus the kettle plus the table it's sitting on and say that is one thermodynamic system. So you can really choose your own system. Honestly, just think about it as an object. That's fine. But yeah, like what this equation tells you is that the total energy that's contained within the object itself is going to be its total kinetic energy plus the total potential energy. So here, what do those terms separately mean? Well, when it comes to the total kinetic energy, the total kinetic energy of that system is literally just the average kinetic energy multiplied by the number of particles. So don't forget, right? The average kinetic energy is the definition of temperature. This is a statement that I really need you guys to remember. I'll say it again. Temperature is defined as the average kinetic energy of those particles inside your object. So the total kinetic energy then depends on effectively the temperature multiplied by how much stuff is at that temperature. And that's pretty reasonable, right? If you have the same amount of stuff, but they're at a high temperature, you have a higher total kinetic energy. If you have the same temperature, but more of that stuff at the same temperature, then once again, higher total kinetic energy. Cool. So that's the first term there. And just have a read of this question. And we'll go through this in like 1 minute.
Wait, will the question give us the potential energy? The total potential energy?
Oh, when it comes to this, like this equation, you will never need to make a calculation with this equation. This is more so just a way of thinking. So, yeah, I'll talk a little bit more about how to use this later. Does anyone need more time looking at the question? Okay, cool. Let's go through it. So we have a container of particles at a certain temperature. And I'm going to add more particles of the same kinetic energy. Will that increase the temperature? No, that will not. Yeah, so it will actually be the same temperature still, because temperature is the average kinetic energy of particles, right? So if you have all of those previous particles at a given temperature, so they're at a given average kinetic energy, and then you add in more particles with that same average kinetic energy, then it's not going to change.
Which means the average doesn't change at all. Yeah.
Okay, now would this increase the internal energy? Well, same thing, yeah. But yes, it would increase the internal energy because now you have the same average KE, but you have more stuff at that same temperature. So you have more total kinetic energy, therefore more total internal energy. Cool. So this here is just to check that you guys understand this concept of total kinetic energy. Now we can move on to the next term, which is the potential energy. So potential energy is a pretty interesting one, right? When we think about potential energy, we usually think about the separation between particles. So if you remember for gravitational potential energy, right? Like let's say here I have my bottle, it's got a certain GPE. I lift it further off the ground, it's got a high GPE now, right? So What that tells you is that potential energy, it's related to position. It's related to the separation between my bottle and the earth. Where greater separation means greater potential energy. So here the same idea. If the particles are more separated, then that means higher potential energy. Now, we have 3 states of matter: solid, liquid, and gas. Which state do you think has the highest potential energy? Gas, right? Because for gas, like everything's kind of just floating around. It's very low density. So there's a lot of particle separation as a gas. So that means very high potential energy. And of course, the lowest potential energy, that would then be your solids, right? Everything's packed really close together. There's very minimal particle separation, and therefore that state has the lowest potential energy.
Watching his Minecraft videos and everything. On everything's line. On everything.
Well, good, because next term is year 12, and at that point you better be locked in, because if you can like think about it, if you can be a whole module ahead by the time you actually enter year 12, then you free up so much more time to tackle maybe like English or something.
Cool.
Right?
TBT got me for that one.
Yeah. Why?
Huh?
Wait, why is it like dotted lines?
Oh, I just didn't really know what to write here, because it's like the middle for like liquid has the middle PE between gas and solid. But yeah, just yeah. Okay, so what's the point of learning this thing? Well, when you transfer energy in to a system, what you do is you increase the internal energy. Right, so let's say if you, yeah.
Is that a U or
This? I'm sorry guys, my handwriting's not that good. But yeah, like when you transfer energy into something, you increase its internal energy. So if you have that kettle and you're boiling the water, then what you're doing is you're increasing the internal energy. Or like if you have something in the microwave and the microwave's going, you are increasing the internal energy. Now, what is the result of that? It's either a change in temperature or a change in state. Okay, like you can look at this formula mathematically. If I increase the internal energy, then either the KE total or the potential energy total has to go up. So if the kinetic energy goes up, then that just means change in temperature, or higher temperature. And then if the potential energy goes up, then that means we get a change in state, say from liquid to gas. Cool. All right. There we go. Yeah, so this slide is just kind of putting what I said into a little bit more words. So you transfer energy into a substance. It will lead to either a increase in temperature or a change in state. But the important thing is that it will never be both of them at the same time. So while you are changing the temperature, there will never be a state change. And while you are engaging in a state change, there won't be a change in temperature. So we're going to look at this graph next that kind of brings this idea together and explains why we don't really have both at the same time. But yeah, I'll just give you guys some time to write stuff down. Looks like you guys are busy writing. Okay. Has Jaden sent a text to admin yet? No? Okay. That's fine then. He can collect it another day.
Wait, you can probably collect it next week. Oh wait, you're not here next week.
Yeah. Oh wait, how do you know?
It's on the Zang.
Oh, it's on that. Yeah, yeah. Sorry guys. So next week, I actually have a uni event on. So it's at the same time, which is why I can't be here next week.
What uni
Uh,
event is that from 7 to 9 p.m.?
Would you guys like to guess? It's actually sorry.
Okay, nothing.
The drinking men thing.
The drinking men thing. What do you mean, bro? We met students. Why would we engage in something as vulgar as drinking? That's crazy. You know? Yeah, yeah, yeah. It's it's a cruise.
What? Okay.
It's like
Red Chris.
yeah, yeah.
You're gonna be saving, bro.
Huh? Am I gonna be what?
Nothing.
We're gonna miss you.
You're gonna drown people off purpose and save them.
2 weeks. 1 week. I don't know.
But yeah, like if you guys want the consistency of like me teaching both topics, you could consider like watching like the Monday lesson if you want to. But that's at Chatswood, so it's a different campus.
How would be the
I don't, no, you can ask Abin for the video, right? Yeah, I'm happy to give the link to you guys if you want to.
Take the class next week.
Who will take the class next week? Yeah. I'm pretty sure it's Alex coming in.
You'll see, bro.
Oh, you'll see.
What does that mean?
No, you'll see.
No, like when it comes to Alex, like I've never been personally taught by him, but I'm pretty sure his like teaching style is a little bit more like technical in the sense that he goes into like more like specifics, and that's because he majored in physics in uni as well, so he of course wants to talk about those things. So yeah, it's just up to if you want something like that.
Is this the guy?
He graduated from King's.
Oh, he was in Junsia.
Yeah, Jun's, yeah, exactly. Yeah.
Wait, Jun went to Kings.
Yeah. Okay, I can.
Anyways, guys, getting a bit off track here. So if we look here at this graph, right, what we have is on the x-axis, increasing internal energy. So how do we get an increase in internal energy? We can do that by continuously heating this substance, right? So as we go across the x-axis, we are applying more and more and more and more heat overall. And then the y-axis here is just the temperature, right? So what we see here, first of all, is that as we increase the temperature more and more, then our solid increases in temperature. So just to make this less abstract, let's say it's like ice, right? So maybe we have ice that starts at like -10 degrees Celsius. And then, I mean, any guesses what the melting point is? Yeah, 0, right? So that would be 0. So pretty much, until you get to a melting point or a boiling point, all of the internal energy increase will go into changing the temperature. And then once you get to a melting point or a boiling point, then all of the energy goes into the state change, and temperature, you can see, doesn't change. Right? So notice how this bit here, this bit is melting. When it comes to like state change, it's always characteristic that the line here is going to be flat. Right? So what this flat line tells you is that you're still putting more energy in, but there's no change in temperature.
What does that say? That minus.
Sorry, -10.
Oh.
-10. Don't worry, like you're not the only one. Like I think I've told some of you guys this, but like my English teacher, in one of my year 12 essays wrote like your letter formation impedes the clarity of your response, like verbatim. Yeah. Anyways, so yeah, this part, all of the energy is going into ripping those particles one away from the other. And if the energy is going to doing that, it won't be going into increasing the speed of those particles. Right, so over here, what we have is 100% ice. And then over here, by the end, it's now 100% water. In the middle, of course, is like 50-50. Right, but the whole point being, once everything is melted, everything's ripped apart, it's all liquid now, then any additional energy increase will lead to a temperature increase once again. And that trend will continue until we hit what point? Until we hit the boiling point, right? At which point it becomes a flat portion again, turning liquid into gas. And once all the liquid has been boiled into the steam, then we can get like further temperature increase that way. Yeah. So yeah, this is the graph that we'll come back to at the end of the lesson as well. It's a really important graph that brings together everything. But just note that the slanted lines, those are the temperature changes. Flat line, that's always a state change.
Is there something like special that happens to like water particles at like that specific temperatures of like 0 degrees and 100 degrees Celsius that results in those changes rather than increasing the temperature?
I think it's more so just that like at those points, we've kind of like reached the threshold where the intermolecular forces between those particles can no longer hold them together. And so any additional energy, like if at that point, the intermolecular force can barely hold it together, then it makes sense that any additional little bit of energy will mean the particles just like rip right off.
So it's a chemistry solution.
I guess it kind of is, but if you look at like all the chemical concepts, they all boil down to physics concepts anyways. Yeah, that's why you see the overlap. All right, so guys, would melting ice be an exothermic or endothermic reaction? Exothermic? All right, let me think about this. Like, I don't memorize this. I think about it every single time. So when it comes to melting ice, right? So melting ice is turning solid into liquid. So we're increasing the particle separation, right? Which means we are raising the potential energy. And for that, we need to put energy into the system. So I think it's endothermic, isn't it?
Wait, if it feels warmer, then it would be exothermic.
If it feels warmer, then it will be exothermic. So melting ice, if you have ice on your hand and it melts,
that means
it feels cold. So therefore, it should be endothermic. Yeah. Come on, boy, let's focus up. So when we're freezing, right? When we freeze something, we have to take away energy from it. We have to reduce its potential energy. So if we take energy away from it, that energy then gets dissipated into the environment. Hence, it's exothermic. So if you guys know, like all of the fridges, they're all hooked up to this like giant fan or whatever. And if you stand behind it, it's actually quite warm. If you look at like AC units as well, right? Like there's like an outdoor part of the AC unit. If you stand in front of that while the AC is on really cold, then that'll actually feel really warm because it's extracting all the hot air from your room. Okay, so does temperature change during melting? Yes or no? No. Does temperature change during freezing? Yes or no? No. Very good. Okay, so we're ready for some calculations now. I guess like just so you guys know, we have these two concepts, heat capacity and latent heat. Heat capacity is related to temperature change. Latent heat is related to state change. Right. So just to get started with, copy down these two lines of definition, please.
Jerry, in your opinion, what's like the hardest one?
I think like the hardest questions often come from module 6 because it's the most heavily conceptual module. But in module 7 and 8, you can also get some like extended responses like 7, 8, even 9 markers. And those can be tricky to write for as well.
Do you like memorize a response?
No, never. Because the questions are always different. You definitely shouldn't memorize a response. Because if you don't answer to the question, then
Is there like a structure you follow to it? Or?
yeah, for sure. Like when we get to year 12, I'll like talk about structures and stuff.
Bro, ChatGPT is not helping.
Yo, what did you say? What are the allegations?
It's not helping.
What are the allegations?
What about like your left?
What about year 11?
We won't get extended response.
Year 11, pro mod 2. At the very least, mod 2 is the most useful one when you go into year 12. Yeah. Mods, yeah, like mod 2 is like forces, momentum, and also energy. That's mod 2. But mod 4 is pretty useful as well. Like mod 4 is electricity and magnetism, and mod 6 is electromagnetism. Not really. In fact, guys, the first stop point of module 6 is literally just module 4 from year 11. Yeah, well, in year 12 we don't really get that.
For first, we do 1, 3, maximum.
Alright guys, let's go through this idea of heat capacity. Hello, happy for you guys to talk, but only after we understood everything. Alright, so we have specific heat capacity and heat capacity. When it comes to specific heat capacity, this is a term that just accounts for the material, whereas for heat capacity, it accounts for what material we're looking at, plus the mass. So how much of that material as well. Yeah, so specific heat capacity, it's related to how easy it is to change the temperature of something. Where if you have a higher heat capacity, it means it's harder to heat up. So you'll need more joules to heat up the same thing by 1 Kelvin. The way I kind of like to think about specific heat capacity is that it's kind of like inertia, right? If you have forces, you can apply the same force, but for a heavier object, that'll result in a lower acceleration. So here, same thing. You can apply the same amount of energy, but for an object with higher specific heat capacity, that'll result in a lower temperature change. And it's actually in both directions as well, right? So substances with higher specific heat capacity, they are actually harder to cool as well. Yeah, so that's why it's so good to think about it as inertia. It's just resistance to change, right? High heat capacity means a lot of energy needs to be input or extracted for the same temperature change.
There's more molecules, more particles.
It's not really about the number of particles necessarily, because you can have like water and you can like turn into ice, and then that will have a different specific heat capacity.
Ah, so it changes like the state of something.
Yeah, it does change depending on the state as well. Yeah. Okay, next, when it comes to heat capacity, it accounts for the mass as well, right? So when it comes to heat capacity, it's looking at the material, but also how much of that material there is. So for example, you can have like 1 liter of water, 100 mils of water. They both have the same specific heat capacity, but the one that's 1 liter, that will be high heat capacity because there's more of it. You need more energy to heat up 1 liter of water compared to 1/10 of that. Okay, so these two amounts of water, they have the same specific heat capacity, but in terms of heat capacity, 1 liter of water has higher heat capacity, precisely 10 times more, okay? All right, let's move on now. So, yes. Yeah, of course. Wait. Why would it be harder to cool? Because Okay, so imagine something where you had to put in 100 joules for it to go from this temperature to that temperature. If you need to go from that temperature back to this temperature, you need to eject 100 joules. Right, so if you have something with even higher heat capacity, then you needed to inject 200 joules to go to this temperature. And so to go back to the original temperature, you need to eject 200 joules. Right, so if it's harder to heat, it's also harder to cool.
So it's like I was going to say something. An object with like a larger mass is harder to decelerate to back to static equilibrium, and then it's harder to move out of it.
Exactly. Yeah. Yeah. Same idea.
Whereas heat capacity is also like acceleration.
Yeah.
Yeah, probably don't have.
Okay. So onto the heat capacity equation now.
That's why you didn't get
Guys, have we seen this equation before?
Yes.
Okay, lovely. So this is on the data sheet, which means you don't need to memorize the equation. But if you want to memorize it, you can memorize it as like Q equals to M cat, right? Because the delta looks like an A. But in terms of the terms here, Q is the amount of energy added or lost to that system. By the way, does Q, like the definition here, does it remind you of a term we learnt about earlier? Yeah. That's a little bit different.
Oh, that's you. Wait,
Yeah.
no one.
Yes. So here we have heat, energy transferred, right? So heat is a process with units of joules. And then M, that's the mass of the thing you have. C is going to be the specific heat capacity. Yes.
What change in temperature? We use Celsius, not Kelvin. Is there a reason for that, or?
Yeah, I'll like talk about that in a second. Yeah, so that's the mass. C is the specific heat capacity. They'll usually give you that value for the specific heat capacity. And on your data sheet, they'll also give you the value for that of water. Okay, so lastly, the change in temperature. That's the change in temperature from the amount of energy added or lost. Now, what unit to use here? You can use Kelvin, or you can use degrees Celsius. The reason why in this one you can use either unit, does anyone want to tell me why?
Increase in say increments.
Yeah, because they increment the same way, right? If we're looking at changes, remember 1 degree Celsius change equals to 1 Kelvin change, right? So if we're looking at changes, then it's actually the same whichever unit we want to use. So it's quite flexible. But this is one of the rarer equations where you can actually do that. For almost every other equation involving temperature, you do have to use kelvins. Okay, cool. So I guess here, notice how we have the specific heat capacities of different substances. The most interesting thing to notice here is that depending on the state that the thing is in, you can have different heat capacities, right? All three of these is H2O, but at different states, different heat capacities. Cool. So a quick exercise for you guys, just based on that equation, and look at here, specific heat capacity of water, that's from your data sheet. Yep.
Oh, are we calculating from you?
Yes.
kg. Yeah. No, you kg. Yeah, kg is I said volume. Kg and units.
No. K.
It is, bro.
You should
Wait, you're right.
I am right. That's what I'm saying.
Isn't that only for water?
Oh. Okay.
Stop talking, man. Stop talking.
Isn't it due to like concentration or something?
What did you say?
Wait, Jerry?
Yeah.
Is the reason why 1 liter of water is the same as like 1 kg of something else due to like the concentration of water?
I'm actually not sure why like exactly 1 ml of water is 1 grams. Like maybe it was just calibrated that way as well. Because like for the Celsius scale, it's suddenly calibrated with water in mind. So I wonder if this is the same.
They just love water.
KG calibrated like a single wall.
Yeah. Like they do use that, but I wonder if that's based off water.
No, that was pretty. Wait, Jerry, why can't you just like put water in a beaker? Just like imagine the beaker is factory, you get the mass, and then you just divide it by the volume.
Yeah, but you can do all that.
To what find
The density of water.
the density of water.
Going to be 1 gram.
What?
The density of water is going to be 1 gram.
No, like the density would just be 1. For water.
I guess so. Yeah, I guess so. Fair enough.
What is like? I mean, like you prove it within itself.
You don't know. You don't know.
Oh, right now. Oh, we wouldn't know that.
Wait, we don't use kilojoules, we use joules for energy, right? Joules or kilojoules?
Joules for energy. Yes.
Kilos times 10 to the 3.
Ding 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 ding.
Okay.
No, I got you.
Okay, so apparently 1 mil is defined as the volume occupied by 1 gram of water. So it is like kind of defined in terms of water. So we just really like water. Fair enough.
Do we need to be accurate with sig figs?
If everything's the same number of SF, then you keep to that, but otherwise it's fine.
Add these numbers. Let's see if we see these steps.
Oh, what? Why are you so ahead of me?
Because I didn't use a calculator.
Oh.
Wait, why'd you press 22?
Because it's a change, so it's final minus initial. So when you add
Oh, yeah, I didn't write the minus. T.
specific heat capacity, so for this one I'm finding C. Wait, what?
What do you know about triple T?
I don't know.
What do you know about triple T?
Oh, and then you go rank 1 in English, extension 1 and advanced. Go rank 1 for both.
You're right.
Sure you go.
He got 24.
I got 19, but whatever. That's rank 3. Go rank 3 for advanced and rank 1 for English.
What's the units for specific heat capacity? Joules.
Yeah, you can just use this. Yeah.
What's joules per kilogram per Kelvin?
Yeah, if you look at it, it's actually quite reasonable why that's the unit, because if you rearrange this to see the subject,
Oh, okay.
then you'll see it's like this, right? And then the unit for heat is like joules, unit for mass is kilograms, for temperature is kelvins.
Why not abbreviate it like for a new?
Yeah, I know. I don't know, like perhaps you can propose that and they'll name it after you.
Roy Papa Jerry.
Wait,
Don't
you mean
specifically know like what James Joule did like with his paddle wheel?
Sorry, say that again?
Don't like specifically know what the guy did with the paddle wheel.
With the paddle wheel?
Or like the interconversion between heat and kinetic.
Yeah, what about it?
Do you need like know the specific details?
No, no need. Yeah.
Not even as a case study.
Well, you can learn it if you want, but I can just tell you it's not going to be useful for exams.
Like
Like it won't. Well,
He's locked in.
you should ask your teachers how much they care about that point, but I suspect most schools just won't test that point at all.
To the environment.
Just minus the answer you get from the left side, is the answer you get on the right side. And you should get this.
Oh no, it's wool.
I don't have a calculator, so I'm going
It is. How much is she paying for this?
400.
Oh, this one now.
Recycled polyester.
But it's such a
Why, yeah. Plus annoying thing.
Oh yeah, plus you get all this extra stuff, right? This and then like the writing, it's like $50 everything.
You pay for the batteries.
Yeah. Even if you're eligible, you have to pay.
I know, but why would you not? Why?
You have to pay. You want at least.
No, I know, but you have to have one.
You have to pay.
I meant, do you have to have one of these?
No, she tricked me, bro. She said,
She tricked me.
She tricked me, bro. Uniform lady tricked me. She was like, oh, do you want everything that you're eligible for? And she just gave me. And I didn't know what she meant. I didn't know this things, bro. I think it was the writing.
Oh, when are you gonna get the writing done?
So good. Once I get proof, if I get proof.
I'll vote for you.
Do we even vote?
What?
Wait, are you like?
How am I meant to do the working for 4 hours there?
He's gonna get
Yeah, so when it comes to all 4 parts, it's all about just rearranging that one formula we've been learning. I think the one important thing is that for change in temperature or change in anything, it's always final minus initial. Yep, so please write your working like that, final minus initial. Sometimes you will have like final temperature being lower, in which case you get a negative change in temperature. So that's something you can definitely see doing a future question as well.
Wait.
Um,
I think I might have popped something wrong.
By the way, one more nice trick is that you can look at the units they have here for the specific heat capacity and just look at what units they use, like joules, kilograms, kelvins. So if you use this value, it's an indication for you that when you like look at the Q, it has to be in joules, mass has to be in kilograms, and temperature has to be in kelvins, okay?
Oh, I remember.
Yeah, so that's actually a reminder for what units you should be using.
I just can't use a calculator.
Yeah, any other questions here?
Considering
Okay.
Do they denote like capital Q and like lowercase q interchangeably? The
Uh,
previous formula had like capital Q.
Oh, capital and lowercase q, yeah, interchangeable. Yeah. Right, guys, just have a read of this question and have a go at the first part. What I'll do is like after maybe like 2 minutes, then I'll go through the entire question together because, yeah, this is quite a standard question type. Except usually they won't give you the like scaffolding here. It will just be a straight question to see.
Why are you rapping so mean? I figured out how to do it. Right? That's cool, man. It's just like the B's extra step.
Right, so I'll go through how to do part A at the very least. So what we have is we have really, really hot iron, and we kind of dump that in like a bath of water. And what's going to happen, of course, is they are not at the same temperature. Iron is hotter, so iron is going to transfer heat into water until they arrive at the same temperature, until they arrive at thermal equilibrium. So what we have here is we have essentially 2 processes where we can apply the equation Q equals to mc delta T. right? We can apply it to iron to look at, its temperature decrease from losing energy. And we can look at the increase in temperature for water as it gains the energy from iron, right? And those two are actually related. The Q that is kind of lost by iron is equal to negative the Q that is gained by the water. Does that kind of make sense? Because it's like a direct heat transfer between iron and water, right? So whatever iron loses, water is going to gain. And the reason why we have a negative sign here, it's very similar to how last time we looked at this equation. So change in K equals to negative change in GPE, right? The gain in one means the loss of the other. So that's what the negative sign is trying to tell you. Here it's the same thing, right? It's trying to say that whatever is lost by the iron will be gained by the water. So the negative sign is actually very important. Now what that means is we can set up the MC delta T for both the iron and the water, right? So we can set it up for iron first.
Wait, sorry,
So-
why is it a negative? Or what?
Because whatever is lost by the iron is gained by the water. All right, guys, are we happy with this line, first of all? Okay, so let's start the left side. So mass of iron is 0.133. And specific heat capacity of iron, that's 450. Can anyone tell me what to write for the change in temperature of the iron?
29. Oh,
You sure?
negative 29.
Of the iron?
Yeah.
We're trying to find the initial temperature of the iron, though.
So it's
That's
45
unknown.
minus T initial.
Yes. So it will actually look like this, right? When it comes to the iron, the final temperature it reaches is 45. That's once iron and water have reached thermal equilibrium. Right, so that's the final temperature. And then T is the initial temperature of the iron. That's what we are trying to find. Okay, and then now the right side here with water. How much water is there? 0.476 kilograms of water. And then what about the heat capacity? Well, 4.2 times 10 to the power of 3. And can someone tell me what the temperature here should be?
29, yeah.
Yeah, so I would just do 45 minus 16 in the working. Always format it as final temperature minus initial temperature, right? So they have the same final temperature but different initial temperatures. Cool. And once this is set up, you can then find the temperature itself, the initial temperature of the iron. Cool. So I'll give you guys a little bit of time to find the final count.
It should be negative.
No, but then they should do negative for all of it again. Like the heat of
But isn't
iron.
I going down?
Yeah, but like the initial temperature should be really hot, not really cold.
Yeah, but isn't this the...
That's the initial.
Oh, this is temperature.
So I think I did wrong.
Oh no, I got it.
Well,
It's in change in temperature.
probably.
Yeah, and then the actual temperature.
It's minus.
We're so funny. Do something like what happened? That's all.
Right, so the final answer should be 1014 degrees Celsius.
Because it becomes add, right? Like they add.
Yeah, exactly.
Okay. Thank you.
Yep, so guys, like this question type here, it's really standard. This is the one that you have to be able to do with absolute confidence. Yep. But all it is, the hardest part I think is maybe like thinking about this first line. But once you've seen this first line once, you you can just remember it.
And do we always keep it Celsius or do we?
Well, it depends on what they give it as. If they give it as Celsius, given that for this equation we can keep it in Celsius, then I'd say just keep it in Celsius.
So it's like conservation of momentum and the change in kinetic energy equals a negative change in GP.
Yeah, it's kind of like those formulas, exactly. Yeah. But I'd say it's more like the change in K equals the negative change in GPE formula. Right, any questions here? Any questions here, guys? Yeah?
Yeah, a calorie DPA. Oh,
Okay,
no.
Did you need something?
No.
you sure?
Yeah.
Okay, everyone, okay, well, make sure you understand this question time. Okay, so that's probably like the hardest part of the lesson out of the way. We have latent heat next, which, if you remember, is related to state change. Cool, so don't forget this graph from earlier, right? What we've done just then is we looked at how energy transferring in can lead to an increase in the average kinetic energy, which is the temperature. And in that case, we discuss heat capacity. So that gets you these slanted portions of the graph. Yeah. The next thing we'll look at is about this straight portion of the graph. It's about how the energy input is going into changing the separation of the particles while the temperature itself doesn't change. So that's going to be the idea of latent heat. Right, so once again, just some definitions. I'll just give you guys a second to copy that down.
Jerry, how would you change the state without changing the temperature?
How would you change the state without changing temperature?
Yeah.
So remember when temperature goes in, it can either like raise the kinetic energy or the potential energy. When we are at like, say like melting temperature, then all of the energy going in is going to be used to change the state, and so it's not used to change temperature. Okay, cool. So specific latent heat, it's the energy needed to change the state of 1 kilogram from like state A to state B. And there's kind of like two names we give it. So we talk about the latent heat of fusion and the latent heat of vaporization. So latent heat of fusion is going from solid to liquid, or more precisely going between the two. Because if you go from liquid to solid, you will also be using the latent heat of fusion. But of course, you just you expel that energy as opposed to getting that energy. All right, and then heat of vaporization, that's going between liquid and gas. So just a very practical example here. If you look at water, we have the specific latent heat of fusion and also specific latent heat of vaporization. And they are going to be different values, right? So depending on which state change you want to calculate, you have to pick out the right value there. And just remember, all of the state changes will happen at certain critical temperatures, which we call the melting temperature or the boiling temperature. Okay, once again, guys, which changes of state are exothermic? Which ones release energy? Liquid to solid, yep. So gas to liquid to solid. They are all going to be exothermic because as you go towards a solid, you decrease in particle separation. And when you decrease in particle separation, then you release that excess potential energy as heat, so exothermic. Now, which one's an endothermic? Of course, it's then going the other way, so solid to liquid to gas.
Yeah, because they have to absorb energy to increase.
Yep,
the
exactly.
Could you
Exactly.
explain that? Okay.
This part?
No, like the change in the particle separation leading to like.
Yeah, okay. So for this case, yeah, that's definitely a bit hard to understand. To go from gas to liquid, everything's coming closer together. It's becoming denser, right? So now there's less particle separation. And so if everything's coming closer together, you lose potential energy, right? And that lost potential energy is actually just released as heat. Hence why it's exothermic. But you can also think about it as like what you did earlier of like, oh, like if it feels hot, then it's exothermic. I think this one's probably like easier to look at. Say like solid to liquid, like ice melting in your hand. That's going to feel cold, so you can tell it's endothermic. And so the opposite of that must then be exothermic.
So this is like specifically where those not specifically where the reactions come from. I was gonna cite them like this is the source of the reactions, like the terminology that we use, but not really.
Yeah, fair enough. All right, so onto the equation as well. This one's also on a data sheet, but you can see it's substantially simpler. So what we have is we have Q, which is the heat once again. We have mass, the amount of substance, and then L is just a specific latent heat. So you choose a specific value based on what state change we're looking at, right? So if we're going from liquid to gas, we'll be looking at the specific latent heat of vaporization. Cool. But yeah, the formula here is much simpler, so calculations are actually relatively straightforward as well. Okay, so one thing to note here is that when it comes to like specific latent heat, sometimes they just refer to it as latent heat, right? So sometimes they might give the L as just latent heat of vaporization or something. In that case, they actually do mean specific latent heat. How do you tell the difference? If you see that the value they give you has per kilograms there, that means it's like standardized for how much of that thing there is, right? Which means it's just considering the material. So if you ever see per kilograms, that will always be specific latent heat, and it's safe for you to use directly.
Q is equal to like mc delta T is
Yep.
regarding the change in temperature when you
Yes.
supply energy, whereas the latent heat equation, Q is the ml, is focused upon what happens in how the state, the physical state of an object is changed with heat by energy.
Yep, correct. That's exactly the idea. All right, quick question, guys.
What's your juice per second? Yeah, juice per second. Oh, so you just multiply it. Okay. It's very small. What? 5500. Beijing. Oh.
Wait, ML.
Wait, and then if it asks you to find the total latent heat, would you times divide the kg?
Yeah. But like this here is the latent heat then, right?
Oh, 38, sorry. You're wrong.
Isn't that the energy supplied?
This?
Yeah.
Yeah. Yes, it is. But it's equal to the latent heat in this case because it's the exact amount of energy needed to change the state of that amount. Yeah.
Well, we can't convert between the two. Like Q.
Well, you can convert between the two by like multiplying or dividing by mass.
Like
But that's it.
between Q to ML and to ML and C.
No, yeah. Like those are describing different things. So yeah. All right, guys. Did we get this answer?
Yeah.
Yep. We're good? Okay. So next piece of theory here is something called a thermostat. This isn't a calculation, it's just a concept. So first of all, what is a thermostat, right? A thermostat is just something that keeps the temperature constant. You can tell from the name, right? Like stat as in like stationary, thermo like as in heat or like temperature, right? So like what do we use it for? Let's say we can use it like this to keep the drinks cold. So this is what we call an ice bath, right? In an ice bath, you have ice and you also have water. Guys, at what temperature can we get both ice and water?
0.
Yeah. At 0 degrees Celsius, we can have both of them coexisting like this. Now let's think about like a thermostat, right? If it's to keep temperature constant, it needs to be able to buffer against heat input and also heat output. So what happens then? Well, if we put energy in, yeah, melt when energy in. So then if you have energy in, it actually goes towards melting the ice. And when there's a state change, there's no temperature change, so the temperature is constant. But what about water? Well, when energy is extracted, then it will freeze. And that too is a state change that buffers against energy being taken out. So in this case, we have a response to energy being put in and also a response to energy being taken out. Both of these responses is a state change in, I guess, like opposite directions. And together what this does is it keeps the temperature constant. So yeah, so it's acting as a thermostat. Right, so as long as you have ice and water, you can be pretty sure that your drinks are kept at the same temperature. If you run out of like one of these two then, in that case, it wouldn't really be a thermostat anymore. It wouldn't be able to buffer against one direction of temperature change. Cool, so this is just like a fun piece of like theory on the side to learn. But yeah, I think the most important part of this lesson is interpreting that graph of like slanted, straight, slanted line, and also doing the calculations, especially with the specific heat capacity equation. Right, any questions with the thermostat? Okay, cool. So lastly, we'll just like tie everything together with, of course, our temperature time graph. So if you guys look at this graph here, this is kind of the full process. We start with ice, we apply some heat. So x-axis is time, right? As more time passes, more and more heat is being put in. So at first, your ice will go up to this certain temperature, which is what?
I mean, so 0 degrees.
Yeah, which is 0 degrees Celsius. And at this point, we can start this process of melting. When we have melting, all the energy is going to changing the state, and therefore it's not changing the temperature. So we have a flat portion. At this portion, do we have any water? No. At this portion, do we have any water? Yes. Yeah, we only have water here. There's no more ice. All of it got melted. And then once it's all water, then we can once again get that temperature increase until we get to the next critical point, which is what?
Boiling.
Yeah, which is 100 degrees Celsius. And at that point, we can get this process of boiling where we go from liquid to gas. And once everything's fully turned into gas, then it can keep increasing in temperature. Now, I'm not sure if you guys notice, but can you see how here, for the horizontal line for melting, it's actually shorter than the horizontal line for boiling? Have a think what that might imply.
Great amount of energy is required to change the state of liquid to gas.
Yep, good. So this implies that you need more energy, right? You need a longer time to supply the energy to change liquid to gas. So basically, it's harder to change from liquid to gas than it is from solid to liquid. Okay, so that's what the graph is saying.
Is that a higher specific heat capacity?
This is a state change. So is it heat capacity or is it the other concept?
Oh, specific latent.
Yeah, so this is your latent heat. It means the latent heat of vaporization is larger than the latent heat of fusion for H2O. Yep, sorry, next.
Is it also because of the fact that like when you go from liquid to a gas, you're also breaking the intermolecular bonds that are present throughout the structure
Yeah, you are, of course.
further from
Yeah, exactly. It's like a more extreme change. Okay. Okay, so here's a question for you guys. This is probably the final question that is standard that you'll see for exams. After this, we have time for either a challenge question or we can go through some things with the exam.
You would give us multiple steps or just one this type of question?
Like, what do you mean multiple steps?
Like, would it give you like all four on like?
Oh, like in an exam question?
Yeah, like you know how before you said it would just always give you C, but in A, B, and
Like I meant for that specific question. Like for that specific question, I scaffolded for you, but for this one, like this is totally exam stuff.
Okay, so you would. Okay.
That's crazy.
How do you find the T final? Okay, sorry. How do you find the T final, right? Because if you use this formula, you need to change it to T final. Yeah, what's the T final? Oh, initially at 28, finally at 56.
Yeah.
Okay.
And he's like this show, like standing up.
Hey, is that
Where's up?
Yeah, I realized.
I figured the graph. I didn't say like use the graph, like use all information.
You better watch this.
No, but
Okay, but it doesn't
really
really apply.
Just
You
like,
like
go to
you,
grab
so
it.
you haven't been ingrained with the culture yet, so it's like doesn't really
So
apply.
he's trying to say you're like I don't know.
That's his words, not mine.
I would say that. Like, it's fine.
Huh?
For him, do you remember? Whoa. He hanged out with Bungie in that time.
I wouldn't know that.
For him,
Yeah, you know,
Brian,
I guess how big his house was.
But apparently for him, rich. I didn't know that.
He's mad rich.
Holmes used to rock up,
I think so.
rock up to school as if he like lives on the bridge. Like genuinely.
Or like not ironing his shirt and stuff.
Yeah, and
Oh,
like
wow.
fully stunk as well. Smell. Okay, well that's just not casual.
The melting temperature of the sample.
Thank God, everyone's trying.
By the way, now, like right now, if any of you guys have a question about the exam, you can ask. Yeah.
Question 2 of multiple choice.
Question 2 of this.
Oh.
What was your specific question about?
I just don't think any of them are 100 should be the answer.
After that, I just have a question about the thermostat thing again. They all have the same magnitude toward that. I think my value's a bit too high.
Grading it.
Yeah, I think my value's a bit high.
Wait, is it? Gonna take props as they tell me that much on the phone. No, I didn't remember that.
No, there is that much. Yeah, I think that's a fair thing to say. I think like A is the one that's like the first thing, right? Yeah. But the other ones can all be possible. Like could be if they have the same magnitude, they just need to be like offset by the same
I
magnitude.
chose like B or D because it's all opposites, so I just chose one of them as like.
Yeah, I think here for B and C, they are kind of tied together. Because if they all have the same magnitude, that means they can't act along the same line.
Yeah.
So I guess for that reason, like D is what you should have guessed.
Because for like B,
But-
if it's like the same magnitude, one like straight up, and then 120 degrees this way, and 120 degrees this way, like even also. But in that one, it says which one is true. So it cannot work the same magnitude.
So
They do not, it says they do not all have the same magnitude.
yes, that's possible.
So if it's like 30, it can be, if it's like 30 newtons out, and 30 newtons like 120 degrees out, and
Yeah.
120 that's 30. Then
Yeah, then
Do you want to answer yet?
it's like
I get what you mean. I think for that question, yeah, it is definitely a little bit dodgy. What is it? I think like A is the only one that's definitively wrong because it's not multiple. But for the other three, you can make an argument that that they which would work in certain like certain circumstances.
Yeah.
Hey,
So
you try for
yeah, I feel like the only thing you could have done there is like notice that B and C are kind of like tied together, and that one goes to D. But yeah, like that's kind of like a really far-fetched answer.
Yeah.
Would we get a mark?
For 2.
Yeah, because like two, this falls like they're all the same magnitude, not necessarily so. They all have the same magnitude.
Yeah.
It's actually
Yes, because of the three forces,
power
Yeah.
when your power is
and they're all cancelled out. They don't act along the same line.
American
Oh.
seconds.
That's what I put. Because like the fact that there's three forces and if it's an equilibrium, it has to be those three forces.
Yeah.
But the answer is D. They don't all have the same magnitude, which is impossible. Because the net forces are in the same direction.
Yes.
I see what you mean. Yeah, like when it comes to that question, I'd say like don't worry about that. As long as you didn't choose A, then like I think it's practically correct. I mean, I think at this stage, like a lot of the exams have been handed out, so I'm not sure like how much like shuffling of the marks we can do at this stage. But if you want, like you can certainly like add an extra mark for yourself. Like perhaps like maybe for like top 10, like prize money category, then we might like have a look at how the marks might change as a result. But apart from that, you can just note that it's like a dodgy question. Basically. Yeah.
It's not that big. Wait, I think
Power of the heater.
Hey, sorry, bro.
But buddy,
What? No, you sound
that would be hyper hypocritical.
I wouldn't just say it's thick.
So it's not that deep.
I wouldn't say it's thick.
What?
I wouldn't say it's thick. These are the things.
Guys, I can't believe we are still on this. You know, it's been years.
We're not on this.
Okay, good.
It's only this guy.
What does that even mean? Why are you time saving?
I actually don't know if
It's joules per second.
We're the smartest guy who came up with that lyrics, but
What's it joules per second? What?
yeah.
I don't get 56.
Bro, you know, right? He didn't make that shit up.
Yeah, well,
you highly
48
tied
because-
to
Oh,
make
crap.
this song.
Because it's for that. Got it.
Oh no, I made some mistake.
Mate, that guy's this thing.
It's easier to do, yeah, I see what you're saying to do. You divide by 120, but
Mom's and so was the
and then B would be motion capture of
There's some like 4-digit that's like the wings.
48.
0.12.
It's always
We have 400 of this static.
Oh, but I don't like.
so he's my side.
Why would you call it that?
No, in the funny way, he knows him.
It's like how
Yeah, do you actually like me? Like he's in that. Yeah, he's one of the boss there.
Wait, but oh no, Chris like
Wait, he's been nice to me. I don't know what he's been nice to me.
I don't know what.
I'll say Franklin was.
What?
Super fair.
No, it's just a question. Hey, it's actually defending the line of application.
What?
Anything physics as well.
Yeah, okay, but how would you know it? Like other people tell you that.
And you know, see is
He found the group chat with text.
and then
I think that's one of the people think that against you. Against you.
yes.
What do? You just go to the school.
All right, guys, let's go through this question. So when it comes to this question, it's all about graph interpretation. So specifically, for part A, you want to find the power of the heater. So you want to deal with the part of the graph you have the most information for. And that's going to be this first part of the graph, where they actually give you the heat capacity, the specific heat capacity of this portion as well. So in that case, you can use Q equals to MC delta T. Calculate for this temperature change of 20 to 48 degrees Celsius. That's the amount of energy that we needed to put in. And this temperature change, you can read from the graph, it happened over 120 seconds. So that means you needed to supply that amount of energy in this amount of time, which means this is the rate at which you would have needed to supply the energy. And the rate of energy transfer, that is power. Okay? And once you calculate that, that'll be very useful for part C and D. Just quickly, part B. Part B is just a flat portion of the graph. That's always state change. Yep, so that's how you can read off the y-axis. It's 48 degrees Celsius. Now, for C, the specific latent heat of fusion. So specific latent heat of fusion here, Q equals to ml, PT equals to ml. So here when it comes to Q, that's the heat transferred, right? PT is power times time. So that will be equal to the energy that the kettle gives to the sample in this amount of time. Yep, so we just rearrange here for L, which is the which is what we want to find, the latent heat. And for the power at 70, for the time it was acting over, it acted from 120 to 560 seconds. So it's about 440 seconds. And mass is 0.12, you get the final answer that way. And for D, you can do it in a similar way, where you just sub Q, energy transferred in, equals the power of the kettle, multiplied by how long that kettle was powered on for. Okay? Any questions about like any of these substitutions?
Wait, how do you use final time of 40? Is it 6?
Yeah, so that's 600 minus 560.
Why would we use the other one?
What's the other one?
It's the other time, like at the start of.
That's liquid phase. The
Oh, yeah.
solid phase.
Yeah, exactly. So for D, they want the liquid phase, which is this portion. Yeah, before it was fully solid. And this part was melting. Yeah. And last thing, just with the units, it's joules per kilograms per Kelvin. So the way you can tell once again is from here. P times T, that's the unit of joules. Mass is kilograms. Temperature is kelvins. Okay. Alternatively, you can also refer to your data sheet and check the unit for water, and it's just the same one. Okay. Cool. So that's all for this lesson then. If any of you guys have extra questions, feel free to come see me now, but otherwise you are free to go.
I have a question about the thermostat thing.
The thermostat thing? Yep, what about it? Yeah, sure. Let me quickly see if online has any questions. Doesn't look like it. In that case, thank you, Tenyu, and I'll see you next time.
Jerry, do you know